Hey there, welcome to a video discussing linear piecewise functions as part of section 2.7. So we're going to start with an example of a piecewise function, and we're going to evaluate it for various x values. So by now you guys should be pretty comfortable with function notation, how to evaluate. So what we're going to do is we're going to find what y equals for a variety of x values. Obviously we're doing it for x equals 0, so that's the side the parentheses for the first expression you see there, and also at x equals 1 and 3. Now the function itself we see off to the left, and it looks a little weird. Actually, you see two expressions for it. What this is telling us is that y could equal two things. Y could equal 2x minus 1 if x is less than or equal to 1, or y would equal something else. So it's almost like it has some sort of identity crisis, if you want to think about it that way. Sometimes a function is this, sometimes something else, depending on what x is. But y could also be 3x plus 1 if x is larger than 1. So again, if x is less than or equal to 1, y is 2x minus 1. If x is greater than 1, y equals 3x plus 1. We have to find f is 0. When x is 0, we have to realize what inequality does it go with. Obviously, it's going with this one. 0 is less than 1, obviously. So you're going to want to plug it into 2x minus 1. So that's what we're going to do. And the output's negative 1. Now for f of 1, I'm still going to use the same expression because the inequality that goes to 2x minus 1 is x is less than or equal to 1, so it could also equal 1. So I'm going to plug into that one as well. And my output's 1 in this case. Now for f of 3, that inequality is satisfied when x is larger than 1. I'm not going to use 2x minus 1 because 3 does not fit with the first inequality. It fits with the second inequality, x is bigger than 1. So it's a condition. So a good way of thinking about it is which condition, and when I say condition, I'm referring to the inequality, is satisfied. And then use the expression that goes with it. So we're going to use 3x plus 1 in this case. So I'll do 3 times 3 plus 1, which of course is 10. So that's how you evaluate a piecewise function. Now, why do we call it a piecewise function? What's happening is that we're taking a piece of each function. We're taking a piece of 2x minus 1, and we're taking a piece of 3x plus 1. So we're actually going to talk about graphing these in just a sec. Let's take a look at number 2. So you have to graph the linear function y equals 3 halves x minus 1 for the domain from negative 2 to 2 for x. Notice that negative 2 is included. Sorry, negative 2 is not included, but 2 is. Well, might help make a little table. If I plug negative 2 in, I will get negative 4. Now, negative 2 is not included, but I still need to figure out what that point is, and you'll see why in a sec. If I plug 2 in, I think I get 2. So I'm going to plot 2 comma 2. But I'm also going to plot negative 2 comma negative 4, and I'm going to make it an open circle or not filled in circle. And because it's just a line with a y-intercept of negative 1 and a slope of 3 halves, there we go. Notice how I only graphed a piece of y equals 3 halves x minus 1. And the piece was determined by the inequality associated with it, which was negative 2 is less than x, which is less than or equal to 2. So that's kind of an example of a piecewise function where you're taking a piece of something. What we're going to do is we're going to take a piece of multiple lines or other types of functions and put it all in one graph. Let's look at another one here. Y equals negative x plus 5. So it's when x is greater than 2. So if I plug 2 in, of course, I get 3. So I plot 2 comma 2. I'm going to make it open because the 2 is not included, right? Just x is greater than 2. Now, we have to do this when x is greater than 2. So if I plug 3 in, for example, I get 2. If I plug 4 in, I get 1. Or you can use the concept of slope. even though slope is -1, right? But remember, you're going larger than 2, so you don't want to do anything to the left of 2. It's got to be to the right of 2 on the x-axis. 3, 2, 4, 1. And it looks like a ray. You do not graph anything else. It's just a piece of y equals -x plus 5. And you have to determine which piece by looking at the inequality that goes with it. So it's determined by x is greater than 2. Let's look at a couple more here. Number 4. You're asked to graph y equals 6. Now, if you want, you could just graph y equals 6. You don't have to look at the inequality at the beginning. So 1, 2, 3, 4, 5, 6. You can just graph if you want. But then you must keep the piece. I know sometimes that means something else, like keeping the peace when two people are quarreling, but different here. Peace, P-I-C-E, not P-A-C-E. So must keep the piece that goes with the condition for x. And the condition is obviously expressed as an inequality. So what's the condition here? X is less than -2. So if I look at where -2 is, which of course is right here, and it's less than, so I need to keep the left of it. So what I'm going to do is I'm going to erase this line and do it again. It looks like that. Notice we keep the part that goes with the inequality. So you would erase the part that doesn't go with the inequality when x is larger than -2. And because -2 is included, we do have a filled in circle there. So let's put it all together in example 5. So you have 3 halves x minus 1 going from -2 to 2. So what I'm going to do is I'm just going to graph, 3 halves x minus 1. You know that the y-intercept is -1, slope is 3 halves up 3 over 2, connected, hooray, we got it. But it's got to be between -2 and 2. So I'm going to erase that line. Let's erase it. Open circle, filled in. And notice how it's only between -2 and 2 for x. You don't do it for y, you got to do it for x because it's a condition for x. Now -x plus 5, if I graph that line, y-intercept of 5. Let's do a different color. Okay. 1, 2, 3, 4, 5. And slope of -1. Now, be careful here. I can't leave it like this because this would fail the vertical line test. Remember, we are dealing with functions. The final result must pass the vertical line test. If it doesn't, then you did something wrong. It's very important. We must pass the vertical line test. So obviously, I have this little red vertical line drawn and it fails. So that's why we have those conditions, the inequalities. I can only do -x plus 5 when x is larger than 2. So I'm going to erase that. The parent's got to start at 2. The 2 is not included. That's okay. Now the 2 is included from the first equation, 3 halves x minus 1. So we'll just leave it filled in because it was already filled in from beforehand. And the slope is -1, so I'll go down 1 over 1, down 1 over 1. Remember, going larger than 2, so it kind of just does that forever. And then I got to do y equals 6, which of course looks like this, but only when x is less than or equal to -2. We did that in actually the previous example. So I don't want that whole line. But I'm going to start it at -2, filled in, and go this way. So notice how our domain is going to be all real numbers. All x values are covered here. But we have to make sure it passes the vertical line test, which it does. And actually, let me do a different color for that horizontal line, we'll use range so it stands out. So we'll practice this in class when we meet again. There are a few more that we should probably look at just to make sure you guys got it. So we're going to take a look at 6, 7, and an 8. So if you'd like to pause the video and see if your graph looks like what I get for number 6. So I'm going to do number 6 right now. But pause the video, come back. Okay, that's how it looks for that one. So again, I graphed a piece of each line, and the piece was determined by the inequality that went with it. Here's another one. We're going to graph y equals x plus 1, but x is going to be greater than -1, so I can't have the whole thing. And it should be open circle. I got to do the other one. That's like saying -x minus 1. That can't be the whole thing. It's got to start at -1 and include. And by the way, this will lead us to what we'll talk about later next week. That graph happens to be the absolute value of x plus 1. We'll have that discussion next week, though. Okay, last bit, number 8, to wrap up the video. We're asked to evaluate. So here x equals 5, of course. Here x equals -5, of course. Here x equals 55. When x equals 5, we're going to use the second expression because that fits with that inequality. So 1/2 times 5 plus 1, get 3.5. Boom, there you go. -5 fits with that one. Get -7. And lastly, 55 fits with the last one, so just straight up 4. So that's a constant. Okay, so we're going to have a discussion on this stuff in class next time we meet and do some practice problems. But this is to help you introduce the concept of linear piecewise functions in general. Okay, goodbye.